Hey everyone, and welcome back. Before we begin here today, please make sure that you like and subscribe because it really does help out our channel, and it also helps us reach others in need of assistance with these topics. So what we're going to be covering today's video is that we're going to be going over differential equations, and we're going to be looking at exact first order equations, and this will be our second part in this series. So what we have going on is that we have to solve this expression shown. We have to find what y equation makes this expression true, given the boundary conditions over here. Now, if we weren't told that this was an exact first order in the title, we would do the following process where we would rearrange this to check to see if it is an exact first order equation. So let's work it as if we're not sure, and let's see what happens. So first thing you want to do is that we want to rearrange to see if this is true. So Mdx plus Ndy is equal to 0. So we will get some expression attached to a dx and some expression of n attached to a dy. So let's go ahead and rewrite this and rearrange it. So we would have y squared minus x squared plus xy, and instead of y prime, I'm going to put dy dx equal to 0. So we're just going to multiply through by our dx here, and what I'm going to do is I'm going to put brackets around our non-dy dx portions. So we would end up with this. We would have y squared minus x squared, and that would be attached to a dx, plus xy attached to our dy is equal to 0. So what that means is that this portion right here would be considered our m. This portion right here would be considered our n. Now, if we did have an exact first order differential equation, the following would be true. That the partial derivative of m with respect to y would be equal to the partial derivative of n with respect to x. So is that true? Well, the partial derivative of m with respect to y would just be the partial derivative with respect to y of y squared minus x squared. And this would just be 2y. Well, let's check the n side here. So the partial derivative of m with respect to x would just be the partial derivative of x of xy. And that just gives me y. Well, these two are not equal to each other. So what does that mean? Does that mean this is not an exact first order differential equation? Well, not necessarily. What this means is that we're going to have to do a little bit of an extra step in order to make this an exact first order differential equation. And what we're going to do is that we are going to try to find what's called an integrating factor. And we're going to try to find an integrating factor such that this is true. So we're going to multiply by some kind of integrating factor to each portion. So we're going to be multiplying it by our m dx and then multiply it by our n dy such that this would be equal to 0 still. And this portion up here of our partial derivatives would also be equal. Now, there are different ways that you can work your integrating factor, but we're going to try one specific method here where we would try this. So what follows here is just our method. So we would have 1 over n multiplied by our partial derivative of m with respect to y minus off our partial derivative of n with respect to x. And let's see what this is. So we would have 1 over xy for our n as shown up here. And then we already found our partial derivatives over here, which is 2y minus off y. And what does this give me? Well, this gives me y over xy, which is essentially just 1 over x. Well, since this portion right here is not dependent on y, we can set up our integrating factor like this. So u of x, not y, it only depends upon x, is equal to e to the power of some fx equation. Well, how do we find what our fx equation is? Well, we can do this. Our fx equation would just be the integration of this portion right here, which is just 1 over x with respect to x. And that gives us the natural log of x. So we can take this and plug it back into our equation up here. And this would give us our integrating factor, which would just be e to the natural log of x. Well, e to the natural log, they cancel with each other here. And you're just left with whatever is attached to the natural log, which is just x. So that means my integrating factor is just x. So to get my new setup, I would have to multiply my m, which is this portion, by x, and the n, this portion, by x as well. So let's go ahead and apply this integrating factor to my original equation, and this would give me a new m and n that I would be dealing with. So this would be x times my original m of x, or y squared minus off x squared dx, plus my original n multiplied by x, which would be x times xy, dy is equal to 0. So let's go ahead and let's funnel through the x here. So this would just be xy squared minus off x cubed dx plus x squared y dy is equal to 0. Now this would be my new m, and this would be my new n. So from now on, whenever I'm writing m and n anywhere throughout the solution, these are the functions that I'm going to be using. So let's go through and let's check our partial derivatives. Well, our partial derivative of m with respect to y would just be 2xy now. And our partial derivative of n with respect to x would also be 2xy now. So now these two are equal to each other. So that means that we can work this as an exact first order equation now, utilizing the integrating factor of x. So now we can actually start our process of solving this differential equation and see what our y equation needs to be to make this hold true. So what I'm going to do is I'm going to set up a dg value, and I will do my best to make sure my g's don't look like y's. So I will set up a dg value, which will be equal to my m dx plus my n dy, which essentially will be equal to 0. So what I'm going to do is I'm going to first integrate g with respect to x and set it equal to m. Because if you integrate this whole thing with respect to x, what you are left with is m. So what this means is that I would have this is equal to my m of xy squared minus x cubed. So let's just find out what my g needs to be. So my g would be equal to the integration of xy squared minus x cubed dx. And then we are going to have to add on a constant. Like with all integration, you have to add on a constant after you work through it. But since we are taking the partial derivative with respect to x, our constant may not just be a constant number. It may be an actual equation that contains a y variable. So we have to write it as h sub y because this constant may actually be a y variable constant. So let's go ahead and let's pull y squared out because we're integrating with respect to x here. So we would have g is equal to y squared, the integration of x dx, minus off the integration of x cubed dx, plus our constant h of y. So not very difficult expressions here to integrate. So we would end up with our equation of g, which is x squared y squared over 2 minus off x to the 4th over 4 plus our h of y. Now, technically, you would also get constants from these integration values here, or these integration processes, but we're just going to lump them into our overall constant of h. So now what we have to do is that since we have this equation of g, well, we have this constant h of y. So let's work on finding h of y, and then we can come back and find out what g is equal to. So what we're going to do is now we're going to take the partial derivative of g with respect to y. So the partial derivative of g with respect to y would be equal to the partial derivative of y of this whole expression right here, which I'm just going to do this to save some room, which is equal to that. And that's not super difficult. We'll just treat x as a constant. So that means that x squared y squared over 2 with the partial derivative of y pops out to be x squared y. This middle section right here, since it doesn't contain any y terms, just goes to 0. And then we would have our partial derivative of our h with respect to y here at the end. Well, what does the partial derivative of g with respect to y actually equal? Well, if we scroll back up, the partial derivative of g with respect to x equals m. So looking at this original equation right here, the partial derivative of g with respect to y would be equal to n, which n is equal to x squared times y. So essentially, what this is going to be equal to is n, which is x squared y. Well, looking at this portion right here, well, we have x squared y on each side. So this means that this term of my partial derivative of my h with respect to y has to be 0. So how do we find h then? Well, we're just going to have to use some integration again. So since the partial derivative of h with respect to y is equal to 0, that means that h will be equal to the integration of 0 dy. Well, anytime you integrate 0, you just get a constant value. So we're just going to call this constant capital B. And we'll use that as a placeholder right now. We won't have to use it very long. So that means that my h equation really doesn't have any y terms in it. It is literally just a constant value. So let's plug this back into our original equation of g up here. So we would have g is equal to x squared y squared over 2 minus off x to the 4th over 4 plus b. Well, how do we find g now, or b? Well, remember that I set my original equation of dg equal to mdx plus ndy. Well, that is equal to 0 right here. So what that means is that dg has to be equal to 0. So whenever that happens, what that means is that g has to be a constant value. Because when you integrate it, you get 0. Or not integrate it, when you take the derivative of it, you get 0. So I'm going to set my g equal to another constant value of capital C, which is typically what you would use for your constants. And you'll see why I did it and why I waited this long to do it. So rewriting this equation, what I have is C is equal to x squared y squared over 2 minus off x to the 4th over 4 plus b. Now I just want to get this equation with one single constant. Well, since I have two constants here, what I can do is I can just take b to the left side here and just have my constant c absorb it, well, because it's a constant within itself. So what I can have here is c is equal to x squared y squared over 2 minus off x to the 4th over 4. Now I have an equation of x and y with only a single constant here. So now I can rearrange and solve for y, because that's a whole goal. What is y equal to? What's my y equation? So let's use some algebra here and rearrange for y. So we would have y squared is equal to x squared over 2 plus 2c over x squared, just using some algebra here. So if we square root each side, we would end up with y is equal to x squared over 2 plus 2 times my constant c over x squared, all of that square rooted. And that would be my y equation. Now, I was given boundary conditions at the start here. Now, if I wasn't given boundary conditions, this would be my final answer. But since I have boundary conditions of y of 4 is equal to 3, this meaning that anytime x is equal to 4, y is equal to 3. I can utilize this boundary condition in order to find out what this constant c actually is and get the true y equation. So let's go ahead and work on this, plugging in 3 wherever y appears and 4 wherever x appears. So we would end up with 3 is equal to the square root of 4 squared over 2 plus 2c over 4 squared, which gives me the square root of 8 plus c over 8. So taking the square of each, or squaring each side, I end up with 9 is equal to 8 plus c over 8. And then if you subtract 8 from each side, you end up with c over 8 is equal to 1, and thus c would have to be equal to 8 here. So this means that my true y equation, my true answer would be this. Y is equal to x squared over 2 plus 2 times c, so that would just be 2 times 8, which is 16, over x squared square rooted, and that is my final answer. Well, you're probably noticing that this video is not yet over, so what else is there left to do? Well, when you're utilizing differential equations and you're solving differential equations here, sometimes it's best to plug back in to make sure that your y equation that you came up with, you did all that hard work for, is the correct answer. So what I'm going to do is I'm going to take this y equation and I'm going to plug it back in to my original equation up here to make sure that everything pops out to be equal to 0. And sometimes the check of a differential equation is harder than the original derivation of the y equation. In this case, it's not so much harder, so let's go ahead and let's check to make sure when I plug in my y equation into this expression here, it does come out to be 0. If it doesn't come out to be 0, that means something went wrong somewhere. So I'm just going to go ahead and rewrite the y equation, the original expression, sorry. So the original expression was y squared minus off x squared plus xy times dy dx. And all of that has to be equal to 0. So let's go ahead and let's fill in our y equation whenever y appears. So we would have x squared, and this will be our check here. So we would have x squared over 2 plus 16 over x squared square rooted, and that first y is squared, minus off x squared plus x times y, which is, once again, x squared over 2 plus 16 over x squared square rooted. And then we're going to have to multiply by the derivative with respect to x of our y. So d dx of the square root of x squared over 2 plus 16 over x squared. And all that has to be equal to 0. So typically, these equations are mostly algebra once you find your y equation, but there will be some calculus involved where you have to find the derivative of your y expression. And sometimes these derivatives can be very complex if your y equation is very complex. This one is not that terrible. So let's focus on the derivative first. So I would have my derivative with respect to x of x squared over 2 plus 16 over x squared. And instead of using the square root, I'm just going to take it to the 1/2 power. So in order to find the derivative of this little expression right here, what I'm going to use is I'm going to use the chain rule. So utilizing the chain rule, I'm going to set up some variables here. And I'm going to set up u is equal to everything inside the 1/2 power. So I would have x squared over 2 plus 16 over x squared. And then I'm going to set up a second variable, which would be v, and that would just be u to the 1/2 power then. So the derivative of this expression in blue would be equal to dv du multiplied by du dx. So we have to find two other derivatives here. So we have to find the derivative of my u equation with respect to x and the derivative of my v equation with respect to u. So let's focus on the easiest one first, and that would just be dv du. So dv du would just be d du of u to the 1/2 power, which is pretty simplistic. It would just be 1/2 u to the minus 1/2. And then let's go ahead and plug in what u is. So we would have 1/2 times x squared over 2 plus 16 over x squared to the minus 1/2 power, and we'll just leave that as it is right now. Then we have to find du dx. We're almost done. We'll have to find du dx. So this one is not terrible. So it would just be x from the first portion, and then the second portion would be just, well, let me just rewrite it real quick in terms of this. So we would have d dx, because I did a little bit of rearranging here. So it'd be x squared over 2 plus 16x to the minus 2. Instead of having it in the denominator there, we'll just take it to the minus 2 power. Now, this is what we end up with. X plus minus 2 times 16x to the minus 3. So what we end up with here is x minus off 32 over x cubed. Well, the original expression would be this then. Once we plug everything back in, because remember this whole ddx thing is going to be the two derivatives that I just found plugged in here multiplied together. So let's take this entire thing that was in here in red, and we're going to simplify down a little bit, like getting rid of the square root for right here because it's squared, and then plugging in my new dv du and du dx into this portion up here. So rewriting and simplifying down, we would have x squared over 2 plus 16 over x squared. The square root is gone because it was squared, minus off x squared from the original expression, plus the original expression of x times y, which would just be x squared over 2 plus 16 over x squared, and getting rid of the square root and just taking everything to the 1/2 power. All of that has to be multiplied by my d du, or my dv du and my du dx. So plugging this in, we would have 1/2 x squared over 2 plus 16 over x cubed to the minus 1/2. And then that would be multiplied by my du dx here of x minus 32 over x cubed. And then all of that has to be equal to 0. So we can do some simplifications here because we have basically a quantity to the 1/2 power being multiplied by the same quantity to the minus 1/2 power. And whenever you have something like this, where it is some variable, let's see, what variable haven't we used? Let's use p. Whenever you have p to the 1/2 power being multiplied by p to the minus 1/2 power, that's essentially just going to be 1. So this whole portion of this right here and this will cancel with each other and just become 1. And then we can simplify down and multiply through with the other ones here. So we would end up with x squared over 2 plus 16 over x squared minus off x squared plus x over 2 from x being multiplied by that 1/2 times my remaining expression of x minus 32 over x cubed has to be equal to 0. And then from here, it is just simple algebra. So simplify it down even further, we end up with x squared over 2 plus 16 over x squared minus off the x squared, and then taking this through, we end up with plus x squared over 2 minus off 16 over x squared is equal to 0 from the x over 2 going into the 32 over the x cubed. And then does this in fact equal 0? Well, yeah, it does, because look, we have 16 over x2 canceling with the negative version of itself. And then we have 1/2 plus another half x squared makes positive x squared. And then you subtract off x squared from that. Hey, look at that. It does work out. It does simplify down to be 0. So the check worked out, which means that the y equation that I came up with in my solution right here is the correct answer, and this is the answer to the differential equation that was given at the start. So that's how you would solve that particular exact first order differential equation utilizing an integration factor. So I hope this video is helpful, and if you want to see more problems solved this Friday, please check out the other videos on our channel. Also, if you haven't done so already, please like this video, leave a positive comment below, and subscribe to the channel because all that really does help us out here. Thank you for watching, and I hope you have a fantastic day.